plenary talk. So it's time to start. Our first plenary talk, our first talk for the afternoon is a plenary talk, and the speaker is Kornell. So whenever you're ready.
For the introduction, I should thank the organizers. I'm a big fan of blast, and I'm a big fan of warm weather, so this is the perfect environment for me. And of course, thank you all for coming to my talk. So this is going to be a talk about dagger symmetric nodal categories, and this doesn't quite fit with the title that I gave to the talk. What happened is, of course, I wanted to plan a talk where I tell you about my results, and then as I was doing that, I realized it was going to be a lot of category theory. Perhaps more category theory than many people here want to hear about. So I decided to adjust the talk and ironically make it about a kind of category. What I'd like to convince you of is that these categories are relevant to your lives, to your research. And I should say that I myself am not a category theorist. My main topic of research is quantum predicate logic, and the reason I think about these categories is because they've been useful to me, so maybe they can be useful to you as well. So, the talk is about dagger symmetric monodal categories. There are a lot of names associated with this class of categories: Doppler, Roberts, Baez, Dolan, Abramsky, Kuka, and Selinger. So I really want to emphasize Selinger's name here because the previous authors were considering this class of categories with additional assumptions. And Selinger was really the person who first focused on exactly this class of categories. Before I get into the definition, the formal definition, I want to communicate some intuition. Dagger symmetric monodal categories should be thought of as generalizing categories, even though formally they're categories with additional structure. And the intuition is that morphisms may have 0 or more sources, and they may have 0 or more targets, and we'll also have an operation that reverses morphisms. So we'll have a way of taking a morphism and exchanging the sources and the targets. This class of categories originate in quantum computing, where they're really great for talking about quantum circuits, but I will argue that they're also natural to algebraic predicate logic. And here I should add a footnote, which is that some of the things that I will try to claim I'm not quite as certain of as I'm certain of the main result that I'd like to tell you about, because I thought about this stuff as a way of preparing this talk. So I believe in what I'm saying, but not 100%. I'm not completely sure. So hopefully, if I say something wrong, somebody here will correct me. So the outline of the talk. First, we'll look at the definition of dagger symmetric monodal categories. Then I'll give some axioms that make a dagger symmetric monodal category the category of sets and relations, and that's the main result I'd like to tell you about. Then I'll give a very short summary of algebraic propositional logic, and here I'll adjust the definitions a little bit, essentially to fit the sort of examples that I care about and that I'd like to tell you about. And then I'll generalize that story to a story about predicate logic. And hopefully that'll give you some sense that these are categories that you too care about. And then I'll finish up with some examples so that it becomes a somewhat concrete discussion. And if something very unexpected happens, I'll also be able to tell you about this analogy, this very interesting analogy between sets and Hilbert spaces, but probably I won't have time for that, so this will be a mystery topic somewhere on the horizon that will remain there. Okay, so first part, dagger symmetric monodal categories. First, I want to tell you about the category rel because it'll be our main example. So it's the category whose objects are sets and whose morphisms are relations. Thus, a morphism R from X to Y is just a subset of X times Y, the Cartesian product. And given two morphisms R from X to Y and S from Y to Z, in other words, given two relations, we compose them in a fairly familiar way, which is to say that A is related to C, just in case A is R related to B and B is S related to C for some B and Y, which is the object, the set where the composition is happening. And the main point of this part of the talk is that with additional structure, rel can be made first a symmetrical nodal category, and second, a dagger category. Probably all of you have seen symmetrical nodal categories, but let me review the definition anyway. Symmetrical nodal category is a triple C times and I, such that C is a category, times is a bifunctor on C, and I is an object of C. And there are canonical natural isomorphisms that are related to the usual defining equations for a monoid. So we have associators, and we have a braiding that formalizes commutativity, and we have an isomorphism that says that I is essentially the identity element for this operation. And these so-called coherence isomorphisms must satisfy certain identities called coherence identities. And if you've seen them, then you know exactly what they are, and if you haven't seen them, then you really don't care. So they're there in the background. I'm going to move on. Rel is an example of a symmetrical nodal category. So to take the product of two sets, we just take the Cartesian product. To take the product of two relations, we essentially take the Cartesian product of the two relations, but we have to reshuffle the elements a little bit so that it fits with the definitions I've already given you. And I is just a singleton. Since we're logicians, we probably want to think of that unique element in the singleton as being the empty set, but it's actually less confusing to give it another notation, so I'm going to write star for it. And of course, the coherence isomorphisms are all familiar bijections that you can ask a student in an introductory set theory course to construct. On to dagger categories. A dagger category is a category C with a dagger operation. So those are the first 2 points. And the dagger is going to be a contravariant functor, which just means that it changes the order of composition when we apply it. And we have 2 additional assumptions. First, the dagger should fix each object. And second, it should be an involution on morphism. So if we do it twice to a morphism, then we should get back to where we started. And indeed, rel is very naturally a dagger category. Of course, if we dagger a set, we get back that set because that's part of the definition. And if we dagger a relation, we really just get the converse of that relation. So we take every pair in that relation and we switch the order of the elements. And the key point of this section of the talk is that these 2 structures are compatible, and they're compatible in a very canonical way that is recognized in other areas of mathematics. So a dagger symmetric monodal category is a quad C times I and dagger, where C times an I is a symmetric monodal category, C dagger is a dagger category, and then we have 2 conditions that say that these 2 things are compatible. So first, the times is compatible with the dagger in exactly the way that you would expect. So if you would take R times S and you dagger it, you get R dagger times S dagger. And the coherence isomorphisms should all be dagger isomorphisms. So they should be special isomorphisms. And here's the relevant definition. A dagger isomorphism is a morphism whose inverse is its dagger. And it turns out that, at least in the setting of quantum theory, this is a very natural definition and a very natural assumption. So now we've put everything together. I've told you about this notion of a dagger symmetric monodal category. I'm going to keep trying to say the words, but these 4 words take up a lot of space on the slides, so I'll end up abbreviating them very often. Okay, that was the first part of the talk. For the second part of the talk, I'd like to tell you about additional axioms that you can put on one of these things to get back the category of sets and relations. So, theorem, a dagger symmetric monodal category C is equivalent to rel if and only if 5 assumptions are satisfied. First, every family of objects has a dagger byproduct. Second, I is simple and separating. Third, each object is dagger self-dual. Fourth, each object X has a unique morphism from I to X with a trivial co-kernel, and I'll tell you about that in just a moment. And fifth, each morphism from I to X determines a decomposition of X into 2 other objects, where this plus symbol denotes the dagger byproduct. So I'll go through what all of this means in just a moment, but I want to give an intuitive gloss for what these properties are saying. So the intuitive gloss is that we're asking for every family to have a disjoint union, every family of objects, that the object I is a singleton, that every object has an equality predicate associated to it, and furthermore, every object has a total predicate associated to it. And by total predicate, I just mean the opposite of the empty predicate. It's the predicate that's everything. And fifth, every predicate determines a subset, and in some sense, this is the most familiar axiom on here, because this is the comprehension axiom. It says if you have a predicate, well, you can take your set apart into 2 pieces, and you get 2 sets. Okay, so let me take a sip of water here, and then I'll tell you about these. So, axiom 1, every family of objects has a dagger byproduct. I won't give you the definition. I'll give you a couple of special cases, and then it'll be clear what the general case looks like. So the dagger byproduct of the empty family of objects is an initial object 0. And recall, an initial object is an object with the property that for any other object, there is a unique error from the initial one to the other one. And because we have this dagger around, it is then also terminal. So it's a 0 object in the usual sense of category theory. And when we have 2 objects, x and y, the dagger byproduct is a coproduct of x and y, where the 2 inclusions satisfy some additional conditions. So we ask that inc x dagger after inc x is identity on x, and we ask that inc y dagger after inc y is identity on y, and we ask that inc y dagger after inc x factors through 0. So that's if we start on the very left side and we go to the very right side, we expect to get a morphism that factors through 0, in other words, the empty relation, intuitively. And then the general story here is that, well, the dagger byproduct of an arbitrary family is a generalization of this. So you look at these 2 definitions, and then you write down the definition that you expect for an infinite family. For axiom 2, we want I to be simple and separating. Here I have to recall what a monomorphism is. A monomorphism is just a morphism M that we can cancel on the left. So if M after R is equal to M after S, then R should be equal to S. And the usual definition of simplicity, we say that I is simple if, first of all, it's not isomorphic to 0. That's sort of a degenerate case. And second, each monomorphism into I either factors through 0 or has an inverse. So intuitively, that's saying that I has 2 subobjects, the empty subobject and everything. And then for separating, we're really saying that this I is the point that all of our sets are made up of. The definition is that if we have that R after V is equal to S after V for all morphisms V from I to X, which is their common domain, then we should be able to conclude that R is equal to S. For the third axiom, we ask that every object is dagger self-dual. And this is just a very special case of the usual duality that we see in monoidal categories. So the definition is that X is dagger self-dual if there is a morphism, eta, from I to X times X, with 2 properties. First, beta after eta should be eta, where beta is the braiding. It's the morphism that's part of the symmetric nodal structure that switches the two factors intuitively. And second, the so-called zigzag identity. Maybe you've seen it, maybe you haven't, but it's this equation, and here we're omitting some associators, some unitors, but it's exactly the equation that one standardly has when talking about dual objects. And in REL, this eta is very familiar. This eta is basically the diagonal. So intuitively, it's just the set of all pairs where the two elements are equal, but we have to throw in this star because we talk about subsets, we talk about predicates as morphisms out of I. For the fourth axiom, we ask that there is a unique morphism from I to X with trivial co-kernel. If you know what a co-kernel is, then you know what I'm talking about. And if you don't know what a co-kernel is, that's okay, because I'm going to say exactly what this means without telling you what a co-kernel is. Here, it's convenient to define a predicate on X to be a morphism from I to X. So in REL, that corresponds to subsets of X. And we always have the empty predicate on X, and that's the unique morphism from I to X that factors through 0. And we always have such a thing because 0 is both initial and terminal, so we always have these two arrows that we can compose. And what we're asking for is a total predicate on X, which, if it exists, is the unique morphism from I to X that satisfies this implication. The implication is that if for any morphism R, intuitively for any relation R, if R after the total predicate is the empty predicate, then it must be that R factors through 0. Intuitively, that R itself is empty. And for our fifth and final axiom, we want to ask that morphisms from I to X, in other words, predicates on X, yield decompositions of X. This is our comprehension axiom. Here I recall a definition that you've seen previously in this talk. A dagger isomorphism is a morphism U such that U dagger is equal to U inverse. And the axiom is that for each predicate V, there exists a dagger isomorphism U that makes this diagram commute. So here at the very top we have V, it takes us from I to X, it finds a particular subset of X for us, and what we're promised is this U that basically takes X and breaks it apart into two pieces where the plus is the byproduct. And so we're factoring V as the total predicate on A, followed by the inclusion of A into the sum A plus B, followed finally by this U that tells us how X looks like A plus B. So the slogan here is that each predicate V yields a decomposition of X into two objects. Those are all the axioms. Let me quickly recap the result. A dagger symmetric monodal category C is equivalent to REL if and only if every family of objects has a dagger byproduct. Second, I is simple. Third, each object is dagger self-dual. Fourth, each object X has a unique morphism from I to X with trivial co-kernel. And 5, each morphism I to X determines a decomposition of X into two other objects, into two pieces. And here I should, I think, make the comment that it would be very interesting to see other theorems of the same flavor. And the proof actually breaks up into two pieces, and it goes via the category of complete atomic Boolean algebras with tense operators as morphisms. So first, we assume all of this stuff, and we prove that we have an equivalence to this category. And then we use a duality theorem to go from this to REL. And one would expect that we should have other results of the same flavor where we have a different, of course, intermediate category of different algebras. Okay, so now I want to tell you a little bit about why you should care, or why I think you should care. And for this, I have to talk about algebraic propositional logic. And the trouble is that probably most of the people in this room know algebraic propositional logic better than I do. So I'll have to adjust the definition a little bit, and if I've missed some core point, then hopefully at some point somebody will tell me that, that I need to do things in a slightly different way. But for the purposes of this talk, propositional logic consists of two things: an algebraic signature chi that contains all of our connectives, and a structural consequence relation on a term of chi, which is just the free chi algebra. A couple of definitions. A consequence relation is a set, for us, a finite sequence, gamma yields phi, with two assumptions. First, gamma yields phi ought to be there whenever phi is an element of gamma. And second, gamma should yield phi if gamma yields psi for each psi in some other set delta, with the property that delta yields phi. And for whatever reason, this definition is usually stated with 3 assumptions instead of 2, but I believe that these 2 are sufficient, and in any case, I was very happy to get a little bit more space on the slide. And then a consequence relation on term of chi is structural. Essentially, if we can do substitutions to valid sequence and get other valid sequence. So one way to say this is that if alpha 1 through alpha n yield phi, then sigma of alpha 1 through sigma of alpha n yield sigma of phi, and this is going to be for each homomorphism sigma on term of chi. So of course I mean a chi algebra homomorphism here. So this is going to be a definition that will adapt to the predicate setting. Now for algebraic semantics, I want to add a little bit of additional structure to the algebras, and the reason for doing this is it's going to accommodate an example that is important for me. So let's say that a chi algebra A is structured when A is furthermore an idempotent monoid with product A1 times A2, and this should really be a commutative idempotent monoid. I thought I had changed the slide, but maybe this is an older version. And then we can define in algebraic semantics for a propositional logic L to consist of a set of structured chi algebras F that make this equivalence true. So we should have that alpha 1 through alpha n yield phi, just in case the value of alpha 1 times the value of alpha 2, all the way through to the value of alpha n, is less than or equal to the value of phi. Of course, for all valuations, so for all homomorphisms, from term of chi to A, and for all A in our family. And here I should say that A being less than or equal to B has the expected meaning, the expected definition. We just mean that A is equal to A times B. So we're thinking of this dot, this monoidal, well, this product on A as being a kind of conjunction that lets us interpret the sequence. Yes, so I apologize. This should have been on this slide. I'm not sure why it's not on there, but I do assume commutativity for this dot. And then for our examples, one algebraic semantics for classical logic consists of course, the Boolean algebra on 2 elements, where the dot is conjunction. And one algebraic semantics for intuitionistic logic consists of all Hiding algebras, with the dot being conjunction again. And then the example that
motivates my looking at all of this stuff. An algebraic semantics for orthomodular logic consists of all orthomodular lattices with A dot B being the meet of A and B. And actually, I have some thoughts about maybe there's a different interpretation of the dot there that would work even better, but I wanted to stick to the story that more people would be familiar with. Here I should emphasize that for orthomodular logic, the usual definition of an algebraic semantics does not work. So we do not have that gamma yields phi, just in case all of the assumptions, all of the elements of gamma being true implies that phi is true for all valuations into all of the modular lattices. So this is the reason why I'm departing from the usual definition, because I care about orthomodular logic and the usual definition doesn't fit. So that's the story for algebraic propositional logic. Now I'm going to try to adapt this story to predicate logic. And of course, there's going to be a lot of categories because we're going to need to replace our algebras with categories. So first I want to talk about chi categories. Let chi be an algebraic signature, again intuitively consisting of all of our connectives. Then let's define a chi category to be a category with additional structure. And that additional structure is that every Hom set should be a chi algebra. In other words, we want to take all of our connectives and we want to be able to interpret all of those connectives as acting on relations between any two objects. And if C and D are chi categories, then we can define a chi functor from C to D to be a functor that preserves this chi structure in the expected way, this algebraic structure. So when we have a functor, what do? We take morphisms to morphisms, and when we're in the chi category setting, we know that we can apply these connectives to each Hom set, and this is exactly the structure that we're asking the functor to preserve. Now, one thing I want to emphasize is we're not asking for the composition to preserve this structure. And the reason for this is very simple, which is if we look at rel, the composition of rel doesn't preserve all of our connectives, so we shouldn't ask this in general. And then one little footnote of a definition. When I talk about a dagger symmetric monoidal chi category, I'm simply talking about a chi category that also carries dagger symmetric monoidal structure quite separately. And again, I'm not asking for any sort of compatibility. I'm not asking that the product preserve the chi algebra structure or anything like that. So we've taken categories, we've added this little twist on them, and now we're going to go through the same story as for algebraic propositional logic and essentially try to categorify it in some sense. So here I want to talk about the category term of chi. So this is going to be all of the terms, all of the formulas that we want to talk about, but they're going to be predicate formulas or really relational formulas. So term of chi by definition is the strict dagger symmetric monoidal chi category that is freely generated by a single object X. So you can look at that sentence and assign it some reasonable meaning, but let me just explicitly tell you what category I'm talking about. We're going to have one object for every natural number. So we're going to have I and x times x and all the nth powers of x. And of course we need some relation variables. So we'll have countably many relation variables for every Hom set in this category. Then we'll need to construct our terms freely. Here are our constants. So of course our relation variables are going to be our constants. We're going to have identities because we're in the categorical setting. We're going to have the braiding, and we'll have whatever constants come from our algebraic signature chi. So chi may have some constants like contradiction or tautology, and we want to be able to interpret that constant in every single Hom set intuitively, because we'll have an empty relation between any two objects and perhaps a total relation between any two objects. And once we have all of these constants, we can build up our terms using composition, using product, and using whatever operations come with chi. So in this way, we generate all of our formulas. And there's a question here, which is, do we really want this to be a dagger symmetric monodal category? Because in a dagger symmetric monodal category, we should have some relations. We shouldn't be able to generate the terms just freely. So one way to do things is to actually impose those relations, because they're not very heavy. Another approach is to say, okay, I'm just going to remember that they should be there, and I'm going to use that to essentially affect the definition of semantics. But this is really a small point, so I don't want to dwell on it. So now I want to tell you about what I mean by predicate logic in this setting. We're going to again go in parallel to the propositional case. A predicate logic for us will consist of an algebraic signature chi and a structural consequence relation, now not on a chi algebra, but on this free chi category that I told you about on the previous slide. What do I mean by a structural consequence relation in this setting? Well, a structural consequence relation on term chi for us will consist of a consequence relation on each Hom set. In other words, we should be able to talk about implications, about valid inferences for any type of relation that we may talk about. And we ask for the usual substitution condition, but now it should be phrased in terms of functors instead of in terms of homomorphisms. So we ask that if we have a valid inference alpha 1 through alpha n yield phi, then sigma of alpha 1 through sigma of alpha n should yield sigma of phi for each dagger symmetric monoidal chi functor on term of chi on this category. I haven't told you what a dagger symmetric monoidal functor is. It basically doesn't matter. It's roughly what you expect it to be. I'll just put up a pseudo definition. A dagger symmetric monoidal functor is simply a functor that preserves the dagger symmetric monoidal structure in a suitable sense. And a suitable sense means, well, since we're doing category theory, we shouldn't preserve everything on the nose. There should be some commutative diagrams that the people who think about these things know about. So a footnote, but we leave it at that. So now for our semantics, I want to tell you about structured chi categories. So a dagger symmetric monoidal chi category is structured first if it has finite dagger byproducts, and second if delta dagger after delta is the identity, where delta is the diagonal morphism from I to I plus I. Now here I want to point out that in contrast to the algebra case, where we were adding structure to the algebra, here we're just making additional assumptions. And the reason it's okay just to make additional assumptions is it'll actually give us our dot product. It'll automatically give us the structure that we need to interpret inferences in this category. So there's a proposition. It follows that well, if we are in a dagger symmetric monoidal chi category, it follows that the category is automatically enriched over these commutative idempotent monoids, and here's how you define the dot. So if I have two morphisms, intuitively two relations R and S, both from X to Y, what I do is I start at X, I follow delta to X plus X, then I put R and S in parallel to get to Y plus Y, and then I follow delta backward to get back to Y. So this is the definition of R dot S. And here there is kind of a surprising, at least to me, twist, which is that in realm, R dot S would work out to be R join S, whereas intuitively we want it to be R meet S, because R meet S is sort of the conjunction of the two relations. So the moral here is that we will need to adjust, well, just slightly to make everything work out, but we'll be justified in doing so. And now for the final slide of this section, let's define an algebraic semantics for a predicate logic L. It'll consist of a set F of structured dagger symmetric monoidal chi categories that make the usual equivalence true. Well, slightly adapted to the setting. So we want that alpha 1 through alpha n yield phi, just in case the value of alpha 1 times the value of alpha 2 all the way to the value of alpha n is less than or equal to the value of phi. And this should be true for all of our valuations for models, really dagger symmetric monoidal chi functors from the term category to all of the category C in our family F. And you could say, well, you said we would have an algebraic semantics, but this sure looks like a categorical semantics, so I feel lied to. And my response here is that compared to the usual categorical semantics story, this story is much more algebraic. We're not talking about monomorphisms, we're not talking about subobjects, we're not talking about pullbacks, we're just talking about constructing terms using basic operations. When I write this inequality, really I just mean an equality between two terms, right? Because this inequality is just an abbreviation for inequality. And you could also say, well, unfortunately, since you're in the categorical setting, some of your compositions are undefined, right? Because we need to type check morphisms before we compose them. But of course, we know exactly how to deal with situations where we can't compose some things that we want to compose. We just add one more element, and this is something that we heard about earlier in this class. So I would say that this is very much an algebraic story, even though it looks, well, also is categorical. So suppose we have this definition, we get some nice things out of this definition. If a predicate logic L has an algebraic semantics in this sense, then we get some nice compatibility between the chi structure and the categorical structure. First, if alpha 1 through alpha n yield phi, then we also have that alpha 1 after psi through alpha n after psi yield phi after psi. So we can compose on the left, we can compose on the right, and we're preserving the validity of the sequent. We can do the same thing for the product. We can take the product on the left, the product on the right, and we still preserve validity. And then we have a variation of this for our plus operation. So now I've told you all about what I think could be called an algebraic semantics for predicate logic. And now I just want to tell you about a few examples that illustrate how I think this machinery should work. So examples. I want to first tell you about the two different composition operations that we have on REL. So we have two ways to compose relations R from X to Y and S from Y to Z. This is the definition that we've already seen, where we say that A should be related to C, just in case A is R related to B and B is S related to C for some B and Y. But there's actually another operation there that I'll denote using the bullet instead of the bubble, which is where we say that A is related to C, just in case A is R related to B, or B is S related to C for all B and Y. So we have these two operations, and I know that Tarski was already writing about the fact that we have these two operations in 1941. I have a very vague sense that people knew this possibly even in the 19th century, but I don't know how far back the literature on this goes. The point, though, is if you're talking about logic in an algebraic way, it's very natural to consider these two operations. And the reason for this is duality. We can get between the two operations in the usual way. So if you have one and you're thinking about duality, you automatically have the other. So we have two categories, rel bubble and rel bullet. Rel bubble is the rel that we've been talking about all along. Rel bullet is this other version of rel with this other composition. And of course, there are isomorphic categories because we can just send a morphism R to the complement of R. And once we have an isomorphism of categories, what we can do is we can move all of the dagger symmetric monoidal structure on rel bubble to rel bullet. So rel bullet itself is also a dagger symmetric monoidal category. And this gets us to the story for classical predicate logic. Let chi be the usual signature. So we'll have conjunction, disjunction, implication, contradiction. Then rel bullet is a dagger symmetric monoidal chi category in the obvious way. And I believe that it is an algebraic semantics for classical predicate logic, while an algebraic semantics in the sense that I've been talking about. And just to give a couple of details as to how this works out, when we go to interpret a formula phi with some free variables x1 through xn in some context, in other words, we order the variables in some canonical way, we interpret that as a morphism from I to the corresponding product of the value of x, where x is the one object in our free term category. Then we know what to do with connectives because we're talking about chi categories, so automatically we know how to interpret connectives. And for the quantifier, we can use this definition. So when we go to interpret for all x1, phi of x1 through xn, really what we are doing is we're evaluating phi and then we're composing it in the bullet way with this morphism. So the empty relation from x to I times a suitable number of identities. So this is how I think the story works out for classical predicate logic. And I want to finish up the talk by giving two more slides like this one for two other examples that I think are interesting and natural. First, intuitionistic predicate logic. Here, I'd like to talk about the dagger symmetric monoidal chi category comp-rel bullet. What do I mean by this? Well, the objects are compact Hausdorff spaces, and the morphisms are open relations. And of course, they should be open relations and not closed relations because we want to interpret intuitionistic logic. And this gives another, I would say, very compelling argument for working with the bullet composition instead of the bubble composition, because it gives us intuitionistic logic as opposed to co-intuitionistic logic, which isn't as natural. And then for the product, we just take the product of the two spaces and we put the product topology on there. So this defines an intuitionistic predicate logic, I would say. What do I mean by this? I mean, look at the substitution maps, really the chi algebra homomorphisms, from the term algebra to the Hom sets of the term category. And it should be the case, I believe that it is the case, that if we start with a valid sequent on the propositional side, then after the substitution, we end up with a valid sequent on the predicate side. And there's an interesting question here, which is, can this intuitionistic predicate logic be axiomatized in the expected sense? which I think is intuitionistic logic for formulas, but classical logic for sentences. And the reason we expect to have classical logic for sentences is because our I will be interpreted as a singleton space. And we know that we'll have classical logic holding there. And this, I think, when we talk about predicate logic, is a very natural assumption. It's an assumption that's at least very natural in the quantum logic setting, where we ask for our exotic logic on arbitrary predicates, but for sentences, we ask just for classical logic. So here's a question for intuitionistic predicate logic. And then for the, well, we'll see if this is the final slide or not. For this slide, we can also ask a question about orthomodular predicate logic. So here we define a dagger-symmetric monoidal chi-category Q-rel bullet, which is a quantum analog of rel bullet. Unfortunately, I can't give you the whole definition in one slide, so I'm going to just say words and we'll nod along, and hopefully everybody will have some sense for what I might be talking about. The objects are hereditarily atomic von Neumann algebras. So these are von Neumann algebras with a particular property. That property is, well, not only is the von Neumann algebra atomic, but when we look at the von Neumann subalgebras of it, those are also atomic. The objects, the morphisms are quantum relations, and here I can really give you nothing more except the citation. So this is a notion defined by Weaver. It turned out to be very fruitful and it's seeing applications in quantum information theory currently. And for x times y, we take the spatial tensor product of x and y. And again, if you know what that is, then you know what I'm talking about. Otherwise, it's some tensor product that is the appropriate one to use here. I'm claiming that this dagger-symmetric monoidal chi-category defines an orthomodular predicate logic. What do I mean by this? Well, I mean exactly what I meant on the previous slide, which is if we look at substitution maps, those are going to preserve validity. And here's a problem that I care a lot about, that I haven't made as much progress on as I would like, which is there a dagger-symmetric monoidal category for orthomodular predicate logic? In other words, I can tell you exactly what the axioms of this should be, but I can't tell you if there is an appropriate category that gives us this predicate logic. So here what we do is, as on the previous slide, we use the axioms of orthomodular logic for our predicate formulas, formulas with free variables. And here it's important to make the assumption that we're talking about non-duplicating formulas. Maybe I should pause and make a comment about that. What do I mean by non-duplicating formula? Well, formulas are built up from atomic formulas. And what we're asking for is that in every atomic formula, we never see the same variable more than once. So if a variable occurs in some place in an atomic formula, then it's never going to occur again in that atomic formula. And the reason for this assumption is, well, the no broadcasting theorem in quantum theory, quantum information theory, that says that you can't duplicate quantum information the same way you can duplicate classical information. So this becomes a very natural assumption to make. And then, as on the previous slide, the usual axioms of classical propositional logic should hold for sentences for essentially the same reason, which is that the monoidal unit has a very simple structure that doesn't require any adaptation of classical propositional logic. I have 1 minute left over, and I probably shouldn't try to cram any slides there. So let me finish. Thank you very much for your attention. The speaker?
last, we had a very nice talk about string diagrams. I wanted to ask if your setting has a nice realization in this realm of string diagrams.
Thank you very much for the question. It is a very natural question to the point that I wanted to talk about that talk specifically during my talk. I decided that there was enough material. The short answer to the question is whenever you have a dagger symmetric nodal category, it automatically comes with a very useful graphical calculus. And that makes it very easy to reason about relations. And it also makes it, I won't say very easy, but easy to reason about quantum gates, which is what it's mostly used for.
Another question? Oh, yeah, we have a question on Zoom. So how do we relate into that? Let me pull it up.
Let's see, for the individual in Zoom may have had a question, could you type in the Zoom chat?
Can you hear me if I speak?
Yes, we can hear you.
Okay, great. Let's do that. Yeah. Thanks for a wonderful talk. So there seemed to be some kind of consensus in the quantum information community that orthomodular lattices and what we used to, quote unquote, quantum logic from the universal algebra lattice side wasn't very helpful because it didn't do dynamics. With your approach, do you think there's going to be some way to get the quantum information theory community interested in orthomodular logic?
Thank you for the question. I would say that quantum logic in the sense of orthomodular lattices is really more useful for foundations than for quantum computation. So I think we should probably convince the foundations people first. And as for dynamics, I think that this doesn't bother me very much for the reason that, well, let's say classical mathematics, classical logic doesn't model dynamics, but I don't think that I would criticize BLAST for not telling us about dynamical systems. That's a little bit of maybe too quick a response, but I think it gets at the main point, which is, well, dynamics is something else, and if we can just figure out the right generalization or the right quantum analog of the logic, that would already be a kind of progress.
Okay, yeah, fair enough. Thank you.
Any other question?
Is there time left for questions?
Yeah, we still have some time.
What are the remaining slides? Can you see them briefly?
Maybe I'll just put them up and make a comment about each one. So for some reason, the clicker doesn't work anymore, which is typical for clickers for a reason I don't understand. If you put the thing down for too long, it gives up on you. So there are 3 slides left. The first of these slides is supposed to tell you what the category of Hilbert spaces is and how it is naturally a dagger symmetric monodal category. And it is naturally a dagger symmetric monodal category, natural to the point that this was actually the motivating example and not REL. So that's the first thing on this slide. The second thing on this slide is this definition of embedding, which was originally given by Hoonen and Jacobs. They use the term dagger kernel, which is more descriptive, but for intuition, I like to use the word embedding in my talks. So an embedding is going to be a monomorphism of 2 different special flavors at the same time. Could we see the next slide? So this second slide has basically one observation on it, even though there's a lot of text, which is if we look at the dagger symmetric monoidal categories, rel and hilb, it turns out that they have a lot of properties in common that are most simply stated in terms of this notion of embedding, which I defined on the previous slide. So a lot of words, perhaps a lot of terms that people haven't seen in a while, but that's not the point. The point is it's a fairly lengthy list that really emphasizes that the two categories are very similar. And then on the final slide, I wanted to tell you about two theorems that say that if you start with all of these properties that rel and hilb have in common, then you only need to add a couple of more assumptions to characterize one or the other. In other words, you take all the common axioms and you add 2, you get rel. If you add a different 2, you get hilb. So let me say what the two are. The first theorem, a dagger symmetric monoidal category C with the properties on the previous slide is equivalent to rel if and only if it has 2 properties. And the properties are first, that every family of objects has a dagger byproduct, and we've seen this assumption before. And 2, every object is dagger self-dual, and we also saw this assumption previously. Now let's throw out those 2 new assumptions and add another 2. We get this result. A dagger symmetric monoidal category C with the properties on the previous slide is equivalent to hilb F, for F either being the real numbers or the complex numbers, if and only if 1, every finite family of objects has a dagger byproduct. So we're still asking for dagger byproducts, but we can't ask for infinite ones anymore. And second, every dagger monomorphism, which is one of the 2 flavors of monomorphism that I mentioned before, every dagger monomorphism is an embedding. So if you have those 2 as your 2 extra assumptions, then you get hilb. And then I wanted to add with a remark, which is that Weaver and others have argued that Hilbert spaces are a kind of quantization of sets. So it's nice to see these two theorems side by side. And just for a little bit of flavor, the idea is, let's say you have a countable set. You can think of each of those elements as a natural number. But if instead you have a separable Hilbert space, then it's going to have an orthonormal basis that you could label by natural numbers. And then you could think of the vectors of that Hilbert space as giving you superpositions of natural numbers. So this is like Schrodinger's cat, except we're talking about different states of a register. Does the register contain the number 3? Does it contain the number 100? Does it contain a superposition of those 2 numbers?
Thank you. I think we're out of time. Let's thank Andrea once again.